All right, so what we're going to talk about in this lesson is how energy is transferred on Earth, okay? And what that looks like in terms of the parts of the Earth that interact, what parts of the Earth are most important for transferring energy, how that relates to climate, how that relates to factors affecting climate and things like that. So there'll be some stuff that'll be incorporated from yesterday, and then there'll be some new stuff. And there'll be some stuff that's probably a review from like junior high, okay? Like for example, what are the 3 ways that heat can be transferred? Okay, radiation is one of them. Okay, if they're in actual physical contact with each other, like in a solid, it's because the particles run into each other. That's called, starts with a C, conduction. Yeah, and then there's the one where they make the currents, convection, right? So those are the 3 methods of heat transfer. Those are going to be important for what we're talking about today. Okay. All right, so we're going to look at the 3 parts of the Earth, understand how energy is absorbed, used, and reflected, okay, and how energy and the Earth interact to produce the conditions necessary to support life. So, okay, those are all going to work together here. All right, so the first part of the Earth that we're going to talk about in terms of energy transfers is the atmosphere. Okay, we talk about it first because it is by far the most important part of the Earth when it comes to being able to transfer energy from one part of the Earth to another. Okay, it's also the part of the Earth that most directly interacts with our main energy source, that being the sun. Right? Now, I'm not going to ask you to memorize the layers of the atmosphere. Okay, they don't really matter that much for what we're doing. Okay, we're just going to kind of look at them here in terms of what happens. But most of what we're concerned about happens down in the troposphere, okay, where we live. All right, so the innermost layer, the troposphere, okay, is where most of our weather occurs. Severe storms and things like that can also be part of the stratosphere. The jet stream is part of the stratosphere, okay, stuff like that. But most of what we're concerned with is the troposphere. That's the lowest 11 kilometers, vertically speaking, of the atmosphere, okay, which means there are places on Earth that you can stand that would be effectively outside of the troposphere. Okay, that would be the tops of the tallest peaks. And if you're on top of Everest, you are essentially beyond the troposphere and into the stratosphere, which is why you can't stay there. Okay, what do they call the top of Everest? Or actually not even the very top, like the last day you're in it. Oh, that's the very bottom. That's where you start. It's called the death zone. Okay, and it's aptly named because when you get up there, the air is so thin that your body is dying every second you're there. Okay, the atmospheric pressure is so low with that. Even with oxygen tanks, it's still not good for your body in terms of the pressure of gases. Oxygen helps you to keep moving, but it doesn't help so much with the changes that are involved with fluid buildup in your lungs. Okay, so if you're in this high pressure or this low pressure area, okay, this high altitude low pressure area, the issues being that you start to get bubbles can start to form in your blood. The gases that are up there that are normally dissolved in your blood can come out more easily. Okay, you become fatigued more easily. You become very dehydrated because as you breathe, you lose so much moisture to the very dry, cold air. Okay, that it creates all kinds of problems. The other part of it is without the pressure of the majority of the atmosphere on top of you, fluid starts to build up in your lungs instead of staying in your bloodstream where it belongs, and that can cause essentially symptoms like pneumonia. Has anyone ever had pneumonia? Okay, like you feel just bagged when you have pneumonia. Now imagine you're trying to climb the tallest mountain in the world carrying a big heavy pack and you feel that way. Okay, that's how those people feel when they're up there. Okay, and it can lead to them making bad decisions that usually involve them sitting down to rest and never getting back up. Okay, most people who die on Everest don't die because they fall. They die because they freeze to death. Okay, that's the most common. So they get tired, they get sleepy, and they're just like, yeah, I'm just going to sit down for a minute. Okay, and then the other people who, like when you climb Everest, you have to walk past them all. Okay, yeah, they use them as markers now. There's green boots and red pants, and like yeah, that's what they call them. They're markers. Okay, and yeah, it's pretty bad if you get up there. Okay, because the conditions aren't right up there for proper energy transfer or for life to exist. It's just not a good spot for us. Okay, but the stratosphere does still play some important roles in that because the air is thinner, it can move a bit faster. Okay, a lot of our wind patterns that can create weather occur there. Okay, beyond that, the other layers don't have a lot to do with energy transfer, but they have to do with the blocking of the harmful things that come from the sun. Okay, the sun spits out all kinds of radiation towards the Earth. Okay, the Earth's magnetic field deflects a lot of that. Okay, the ozone layer just blocks a lot. Excuse me, a lot of the ultraviolet rays and things like that. Okay, but the upper layers of the atmosphere are important for essentially protecting us from the sun. Were the atmosphere a lot thinner, then a lot more radiation would get through. Okay, all right. So the atmosphere is really important because it is the most fluid of the three parts of the Earth. Okay, because the three parts of the Earth are the atmosphere, the hydrosphere, which is all the water, and then the lithosphere, which is all the rock. Okay, the atmosphere is by far the most fluid and thus able to move around than the of the three. Okay, all right. So the atmosphere plays a critical role in maintaining the Earth's temperature, which in turn has a profound effect on Earth's climate. Okay, so the nature of the atmosphere is very important in that regard. Okay, much of the incoming solar radiation is reflected away from the Earth by particles in the atmosphere: water vapor, ozone, particulates. Okay, we know from climate research that volcanic eruption anywhere on Earth, okay, if it's severe enough, can lead to a cooler year the following year, just because of the amount of dust and smoke and ash that ends up in the atmosphere as a result of it. Okay, it can, and it stays there for a long time. It can cause global cooling effect of a degree or two. Okay, for a year to 2 years. Okay, so all those things influence how much radiation comes in. Now, the other part of it is the Earth's surface. Okay, and this particular aspect of the Earth's surface. So this word, albedo, is an important term for us. So you might want to write it down if you don't have your notes in front of you. Okay? Albedo is an important term. Okay? It refers to the reflectivity of the Earth's surface. Something with a very high albedo is highly reflective. Something with a very low albedo is absorptive. Okay, so for us up here, we see the effects of this quite a bit because we have obviously the seasons. Okay, in the summertime, the sun's shining, okay, 70% of the incoming radiation is absorbed by the ground, okay, by grass and plants and the soil and whatever else. Okay, about 10% of it gets reflected off of water bodies, okay, and another 20% gets reflected off the Earth's surface. So the Earth's bare surface can absorb 70% of the incoming solar radiation, depending on what it's covered in. Okay, if it's covered in grass and dirt and things like that, those have a very low albedo, so they absorb a lot of energy. If it's covered in snow, the opposite is true. Okay, because snow is what color? Good, everyone said white, not yellow. We're not talking about that kind of snow. Okay, all right, so white is the most reflective of all colors. It has the highest albedo. Okay, white reflects all colors. So when the sun is shining on the snow, 85 to 90% of the incoming radiation gets reflected. Okay, only 10% gets absorbed. In order for temperature to increase, absorption has to occur. When reflection occurs, nothing happens. There's no energy being gained because it just bounces off. Okay, which is why in the winter, okay, we have such a poor situation energy-wise. First off, the sun is at a low angle. It's only out for 6 hours a day, okay, and the ground is highly reflective, so very little stuff gets absorbed during that time. Whereas in the summer, the sun is more directly overhead, the ground is darker, has a lower albedo, and absorbs way more light. Things are going to be warmer during those months. Okay, everybody with me there? All right, so high albedo, highly reflective. Low albedo, very absorbing. Okay. All right, so we need to know about that because that's going to really influence how much energy is absorbed in an area. Now, really, 3 things can happen to light when it strikes the Earth. It can be absorbed. If it's absorbed, then temperature goes up. It can be reflected. If it's reflected, basically nothing changes. Okay, no energy has been gained or lost, so there's no real change. The other thing that can happen is it can be converted. What's it going to get converted into? What are the only organisms on Earth capable of using the sun's energy directly? Plants. What do they convert it into? Sugar. Okay, so those are the three fates of light when it strikes the Earth's surface, and you're going to need to know those. Okay, the three fates of solar energy are absorption, okay, so if there's absorption, okay, then there will be an increase in energy and temperature. Reflection. Okay, no change in energy or temperature. And then the last fate is conversion. Right? Those are the three things that can happen. So one of the things that you'll be asked to do with this type of an idea, okay, would be if I show you a picture of a place on Earth, okay, I would ask you, what's the light gonna do when it strikes this area? Okay, if I'm showing you a picture of like a glacier, it's gonna be mostly what? Mostly reflected, right? It's very white, it has a very high albedo, not much energy change is gonna happen. If I show you a tropical rainforest, you're gonna say, yeah, well, high albedo and a lot of conversion, right? Because there's a lot of plants there. So those would be the two big things in that area. Okay, so a lot more of that energy is actually being used to do something. Okay, so there's going to be changes in energy and temperature, right? So it's going to get warmer, temperature is going to go up, obviously, and there's going to be a lot of conversion of light into chemical energy by photosynthesis. Okay, so that would be one of the things you'd be asked to do. Another thing you might be asked to do would be to design something that could harness and transfer the sun's energy. Okay, so if I ask you, to give me a basic design for a solar water heater, okay, what are some things you would make about it? It should be black, yeah. Okay, why do we want it black? Because black is a low albedo. It absorbs most of the light. Okay, if you doubt me, in June, park a black car and a white car side by side in the parking lot. And at the end of the day, when you're leaving, put your hand on the white car and then very quickly touch the black car. Okay, don't put your hand on it and hold it there. Okay, because the black car, I guarantee you, will be a lot hotter. Right, it's going to absorb a lot more of that solar energy because it has a lower albedo. Okay, which is why you typically see lighter colored cars in hotter climates because they just don't heat as much. Okay. All right, so I might ask you to do something like that. Okay, that's again applying your knowledge of absorption, reflection, and conversion. Okay, and then I would probably have something else on that about convection, radiation, and conduction, but we haven't talked about those yet. Okay, so there's a lot of application stuff in this unit. All right, so make sure you have those, okay, because those are going to be important. Like I said, there'll be a question on your test where I show you a picture of a place on Earth and ask you about these three things for that particular place. Okay, other things that can happen to the light when it comes through the atmosphere is that it can pass all the way through. Okay, some of it passes all the way through, it hits the Earth and reflects off the Earth. Then it goes back up into the atmosphere, but doesn't get all the way out. Okay, it reflects back down and hits the Earth again. What do we call that? Oh, come on, everyone makes a big deal out of it. Such a horrible thing. Well, not climate, this could maybe be a cause of climate change. Okay? Greenhouse gases. Yeah, the greenhouse effect. Okay. Earth has a greenhouse effect. It always has had a greenhouse effect. It's important that it does. If the Earth did not have a greenhouse effect, it would be an absolutely frozen wasteland. Okay. As an example, Mars has a much thinner atmosphere, has virtually no greenhouse effect, even though what gases there are is all carbon dioxide. It's a frozen wasteland. Okay. Then you look at Venus, which has an incredibly thick atmosphere. Its greenhouse effect is out of control, and it's hotter than the inside of your oven on the surface. Okay. So you want a healthy balance. We have a pretty healthy balance. Okay? Our greenhouse effect keeps the Earth warm. Now, if the greenhouse effect gets worse, obviously then the Earth will get hotter. Okay? But that's not necessarily a desirable thing. Okay? Other things that can happen to light when it hits the Earth's atmosphere is that it can be backscattered. Okay? That means its path is altered so that it just kind of goes everywhere. Right? What does this cause? What does backscattering of light cause? This one will probably surprise you. Why is the sky blue? It's like that, yeah. It's actually the backscattering. Okay, the composition of our atmosphere scatters blue light. And so the blue wavelengths of light, when they hit the Earth's atmosphere, just kind of go everywhere, okay, in random patterns, making the sky appear blue. Okay, I know that somewhere along the way somebody told you it's because the sun reflects off the ocean, but the ocean looks blue because it reflects the sky, not the other way around. Okay, the ocean is actually what color? It's clear, yeah, unless it's really dirty, but it's clear. Okay, so the ocean's not blue, it just looks blue because it reflects the sky, which is blue because of the backscattering of blue light, right? Which is also why at sunrise and sunset the sky looks orange. Okay, when the sun is lower in the sky, it's passing through a thicker part of the Earth's atmosphere that contains different stuff. Okay, the higher parts of the Earth's atmosphere directly overhead are fairly clean. But when it's low on the horizon, it's now passing through dust, smoke, and other particulates that scatter red and orange light instead, okay, making the sky appear red, orange, that color at sunset. Making sense? There, you learned something new. Shattering preconceptions about the sky being blue. All right. So does that make sense? Those are some of the things that can happen, okay, when the light is coming through, okay, and all of these things, okay, if there's any absorption, that's going to lead to an increase in temperature, okay. The atmosphere does absorb a fair amount of the solar radiation that comes in, and that helps it to warm up. Okay, gases present in the Earth's atmosphere, like we said, can help to maintain the Earth's temperature and climate. Carbon dioxide, CFCs, methane, ozone, nitrous oxide all allow incoming radiation through, but they trap it. Okay, it can't get back out. And if there's a lot of these in the atmosphere, then we build up a greater greenhouse effect than normal. Right? Like we said, a greenhouse effect is important. Without it, the Earth would be a lot colder. Okay? All right, and so that's just this diagram here. Okay, we can see that some of it gets back out and some of it gets reflected back. All right. So CO2, obviously we know that's CFCs are chlorinated fluorocarbons. Okay, we're trying to eliminate those from lots of products because they're really not good for both the ozone layer or greenhouse effect. So we're trying to eliminate those. Okay, methane, where does that come from? Yeah, it's cow and pig farts. All people farts too. Okay, all farts contain methane. Right? It's a greenhouse gas. It's naturally produced by lots of bacteria as well. Okay, ozone, okay, is actually produced through a couple of different processes, and then it's broken down by being hit by ultraviolet light, and then it has to be replenished. Okay, yeah. So all of those are greenhouse gases, and they're again important. All right, so we talked about the atmosphere. The atmosphere is very fluid. It can move very easily, so it's very important for transferring solar energy. Okay, the hydrosphere, also fluid. As fluid as the atmosphere? No, okay? The atmosphere also surrounds the entire Earth. Does the hydrosphere surround the entire Earth? No, it's in parts of the Earth. It's still an important part of the Earth, okay? But it doesn't have the same range as the atmosphere does. It's still important in terms of transferring energy, though. Okay, so all the water on, above, or under the Earth's surface is known as the hydrosphere. Okay, that's water vapor, okay, liquid water, and ice. Okay, less than 0.1% of all the water that's evaporated from the surface of the Earth is returned to that same spot. Okay, so when it evaporates from here, it is not likely to fall back here. Okay, it's going to go somewhere else. Okay, but by the same token, the stuff that falls here is not likely to have evaporated from here either. Okay. So it can go into lakes, rivers, streams. It can seep into underground hollows. Okay, the rest will return to the ocean or be frozen in polar ice caps or glaciers or things of that nature. Okay. All right, so the important part of the hydrosphere is the water cycle. Okay, now, up until now, you've just learned about the water cycle for its own sake. The water cycle is the water cycle. It's how all the water moves around. Okay, and I'm not saying that's not important. It is. We're looking at the water cycle from an energy perspective. All right. To get water to evaporate, do you need energy? Yeah, and in fact, we'll learn later in the unit, you need a lot of it. Okay, so once we get water into the atmosphere as a vapor, it represents huge amounts of stored energy that we call latent heat. Okay, that moist air containing all that vapor can move from one place to another and take the energy it has in it with it. Okay, so it's another way to transfer energy from one place to another, but it's using water instead of just the atmosphere itself. Okay. So if we're talking about water that evaporates from the equator, because most of the water that evaporates from there, okay, if it moves northward, it's going to bring energy that was absorbed somewhere else to a more northerly area, okay, in the form of latent heat. So when that water then gets to, let's say, us, and then falls as rain, it also releases the energy that was stored in the vapor to our area. Okay, so it brings warmer energy or more energy to us from another part of the world. Okay, all right. So when we're looking at this in terms of energy, okay, we'll start with evaporation. That's an energy input. All right, it takes energy for this to happen. Okay, so we produce water vapor. Same thing for evapotranspiration. Okay, transpiration means it's the result of photosynthesis. So it's water that's evaporated, but from the surface of plants. Either way, both of those represent energy inputs. So now we have this water vapor that contains lots of energy in the atmosphere. Okay, at some point, it's going to fall as precipitation, snow, rain, hail, whatever. Okay, that's going to represent now an energy output. Right, that energy is going back into the system here. Okay, it's going to be more tangible as opposed to latent. Okay, when that water obviously hits the Earth's surface, okay, yeah, lots of things can happen to it. Okay, it can be absorbed into the Earth by infiltration. Okay, that may be a new term. I don't find that everybody always teaches that term. Okay, so you'll need to know that one. Infiltration. Okay, that's how water recharges wells and groundwater and things like that. It percolates down through the soil and rocks and stuff and ends up in people's aquifers. Okay. It can also run off. Okay, we see runoff all the time in the spring. Okay, the rivers come up, they turn brown, right, and all that meltwater comes from the snow in the mountains. Okay, runoff is important. Okay, it represents a lot of nutrients. It represents a lot of energy. Okay, as that water moves through, because now that water is not locked up in a solid form, okay, somewhere else. Do you have to put energy in to melt ice? Okay, so runoff is another energy output. Okay, we're seeing the effect of the solar energy melting the ice, okay, in the form of kinetic energy moving off the mountains. All right, so that stuff will either end up in lakes and rivers, or it'll end up back in the ocean eventually, okay, where the cycle can start again. Everybody good with that? Make sure you know the water cycle. I always put a diagram of the water cycle on the unit exam. Okay, so no evaporation, transpiration, infiltration, precipitation, and runoff. Okay, make sure you know those 5. All right, now most of the Earth's water, 97% of it, is salty. Okay, only a small portion, less than 3%, is fresh, and most of that is frozen. Okay, it's either in the ice caps or glaciers or wherever. Okay, so it's being slowly released, well, more quickly released now. Okay, as meltwater over the years here. Okay, so 3/4 of all fresh water is found in polar ice caps and glaciers. Nearly 1/4, known as groundwater, is found underground in water-bearing porous rock. That's where we get most of our drinking water from. Okay, is from wells okay, around this area. All right, so we can have salty water, we can have fresh water, and we can have ice. Okay, all of them still represent water. Okay, but obviously there's concerns about the viability and availability of those water sources. Okay, many animals can live in this environment. Can we? No. Okay, that salt water is no good for us. So it's a concern because we want this stuff, which generally comes from here. And what's happening to these? Yeah, they're shrinking all the time. Okay, that's the Robson Glacier. So I showed you that picture of Mount Robson yesterday. Okay, that's like right over here. All right, so this is the Robson Glacier. Now, when we did this hike back in 2003, okay, there was this meadow that we were walking through, and there's a sign in the middle of it that says, in 1902, the Alpine Club of Canada marked this point as the toe of the Robson Glacier. In 2003, we stood by that sign and could not see the glacier. So in 100 years, it had receded probably 4 kilometers in 100 years. All right. Now that's just one dimension of the recession. Okay, that's just the horizontal. This whole valley up to here would have been filled with ice as well. So it's not just receding backwards, it's also shrinking vertically. Right? So we're seeing a massive decrease in the amount of fresh water available in the form of ice, okay, over these last, because we're at the end of an ice age, right? Like if you were here standing in this spot, let's say 10,000 years ago, you would have been under a kilometer thick sheet of ice called the Laurentide ice sheet. What's that? Yes, yeah, as the glaciers expanded outwards, to start the ice age, pieces of mountain were broken off and it was pushed out, right? And then dragged somewhat back and then left there as the ice melted around it. Yeah. Okay. But yeah, so what we're left with is these small remnants of that giant ice sheet. Okay? And they're going to shrink. They're going to keep shrinking. Okay? All right. The lithosphere, okay, the lithosphere represents the solid part of the Earth. Now, the solid part of the Earth has the smallest role to play in transferring energy. It has the largest role to play in terms of the absorption of energy and the conversion of energy. Okay, the atmosphere doesn't, it absorbs some, but it doesn't do any conversion because there's no plants living there. Okay, but plants need soil. Okay, and soil is part of the lithosphere. So the lithosphere is really in control of how much energy gets converted and to a big extent how much of it gets absorbed, because this is where the albedo stuff comes into play. Okay, not all parts of the Earth's surface are the same color, same texture, have the same absorbing ability. Okay, everyone all right with that idea? Okay, because we know if you walk on the beach in the middle of the day, okay, under the hot sun, you can burn your feet, right? It's got a very low albedo. It absorbs a lot of solar energy, okay, because it's all those little pieces of rock, okay, that are there. Okay, whereas if you walk on the grass, okay, the grass is much cooler, right? It's converting the energy as opposed to absorbing it. All right, that sort of makes sense. Okay, so like we said, atmosphere important for transfer. The hydrosphere important for transfer, but mostly through the water cycle. Okay, lithosphere, basically no role in transfer, but has a big role to play in terms of conversion and absorption. All right, so that's what we need to remember for that. So the most important part of the lithosphere then is the soil. Okay, that's the layer, the top layer of the Earth's surface where the plants can grow. Soil is different everywhere you go. Right, around here, the soil is very sandy because the bedrock here is made from sandstone. Right. That said, it's still pretty good soil. This is highly valuable farmland around us. If you go a little bit further north, the soil becomes a lot less sandy because more of the bedrock is limestone. Okay? It leads to different types of soils. Okay? So the type of rock that's in an area determines the type of soil. The type of soil can determine what kind of plants can live there. Okay? This is also soil. When you look at it, you think that looks like rocks. Well, that's the topmost layer. I didn't say it was good soil, but it's soil. something can grow in it. Okay, mesquite bushes and sage and stuff like that that are very drought tolerant, it can grow in soils like that. All right, so it's its own ecosystem. It has biotic and abiotic components. We talked about those in Unit 2. Okay, inorganic chemicals, air, water, decaying material, okay, all that kind of stuff is all part of the soil. Okay, and soil is typically broken up into layers. Okay, if you ever dug a hole as a kid, okay, you went through the dirt and then you got the clay, and then if you dug far enough, rock. Okay, I know where my old house was, that was a major issue because there was about this much soil and then there was rock. Okay, like they pulled rocks the size of Volkswagens out of the hole they dug for our basement. Okay, because we were right on the bedrock. There was virtually no soil there. Okay, so depending on where you are, soil can be really thick or it can be really thin, but it typically has 3 layers. Okay, those layers being the topsoil, okay, or the A horizon, the subsoil, the B horizon, and the parent material, which is made of rock, called the C horizon. Okay? We don't actually use these terms here. Right? We just go A, B, and C. Right? Everyone all right with that idea? So 3 layers, okay, that we're most concerned with. Obviously, plants are mostly concerned with this top layer. Okay? What's the B horizon made mostly out of? Clay. Yeah. Why does clay always end up down here? Why doesn't clay stay up here? It's not. It's a little bit to do with density, but it actually has more to do with particle size. Okay, clay, if you like put it between your fingers, is very fine. It feels like flour. Okay, whereas like topsoil, especially around here, feels very gritty because the particles are larger. So smaller particles can wash down between the larger ones, and since clay is made of really small particles, it'll wash down through the topsoil and collect underneath it. Okay, which is why even if like if you had a sandbox as a kid, right, the bottom of the sandbox there always seemed to be clay, right? And trust me, like I've built a couple of sandboxes. I don't put clay in the bottom of them. Okay? It just ends up there because the fine particles, when it rains or whatever, wash through the sand, which is larger, and end up underneath, always creating a layer of clay underneath. Okay? Was the clay, yeah, because you can make a ball and throw it at people, right? Yeah, totally. Okay, so if you've seen like the side of it where a road has been cut out or where they've dug a hole for a basement, okay, you're going to see the topsoil, although not as much around here because typically we peel the topsoil away, okay, before we build anything because it keeps the weeds down. But you'll see then the subsoil, the clay, and then lots of times you'll also see the rock underneath that. Okay, all right. So the A horizon is the topsoil. It's a mixture of decomposed rock, okay, so broken up rock, really small stuff, living organisms, decaying organic material, okay, dead plants and animal feces, okay, all that kind of stuff is all in there. All right, so this would be a typical soil horizon from our area, okay, a fairly dark topsoil, okay, a much lighter kind of B horizon, and then you'd have underneath that, at least for us, mostly sandstone, okay, mostly sandstone around here. Right, so for the prairies, we have really thick A horizons. The reason we have really thick topsoil here is because there's lots of grass. And every year the grass dies. And new grass grows up the following year from under it. So there's always a layer of leaf litter and blades of grass and roots from the year before. Okay, that builds up a very thick topsoil very quickly. Okay, farmers are obviously very concerned about topsoil because they need good topsoil for farming, so they don't want to lose any of it. Okay, what do we call it if you lose topsoil? Erosion, yeah. And erosion can happen through rain or wind. Around here, mostly wind, okay? But occasionally, you can get, big rainstorm, whatever, and it washes away. But for the most part, it's wind. So they want to keep the roots intact in their fields as much as possible because the roots are what helps hold the soil down. It's why you very rarely see a plowed field with just black dirt. Okay? Farmers don't want to leave it that way because if they do, lots of it can blow away. Okay? So they constantly want to have the roots there, which is why a lot of farmers use what's called zero-till farming, okay? Which means they'll just seed the next crop on the stubble of the old, okay? Without actually plowing it up. Okay? It keeps the nutrients there, it holds the soil in place, and it's better. Okay, B horizon has little or no organic matter because, well, there's not a lot of stuff down there. Okay, the roots very rarely get that far down. There's not a lot of bacteria and things in that layer, so it's mostly clay. Okay, if you go to PEI, you get lots of that. Okay, you can get your PEI dirt shirt. Okay, it's stained with the red dirt, okay, of that area, right? So yeah, it's mostly clay, okay, and it's usually kind of a neutral color. Very rarely is it actually this red. It's mostly like a tannish kind of color. Okay, so lots of clay there. If you're in the tropical rainforest, okay, a tropical rainforest typically has very little topsoil. It's mostly clay, which is odd because you would think to grow a forest like that you'd need lots of topsoil, but it's so flooded all the time that the topsoil always washes away. The plants actually take their nutrients right out of the floodwater. Right, and then lastly, we got the sea horizon. You can see the sea horizons, lots of broken rock, and that broken rock becomes more and more solid as the further down you go until you're actually on the bedrock itself. Okay. Why do we call it parent material? It's where the soil comes from. Just like you came from your parents, the soil comes from the bedrock, so it's the parent material of the soil. All right, I'm going to give you a little break here because I've been talking for a long time. Okay, we'll come back, we'll talk about energy a little bit more. All right, so if we're looking at the Earth is a system, okay? Just like systems we talked about in the last unit. It's an open system, okay? It can exchange matter and energy with its surroundings, right? Most of the time it's receiving it because the sun is obviously much larger, right? So we have inputs of solar energy, okay? But we also have some outputs, but they're minimal compared to those inputs from the sun. Okay, so we would have things like maybe geothermal, okay, the possible radioactive decay of, radioactive elements within the Earth. Okay, things like that would be our outputs, but they're nothing compared to all of the energy we receive from the sun. Okay, now, gravity, like we said, magnetism, geological forces, they're small by comparison. Okay, but so is the output of energy that comes from the Earth is mostly the reflected sunlight. Okay, you probably heard when you were a kid, like planets are like big mirrors, right? And that's why we can see them in the sky and why the moon is so bright, okay, because it reflects so much of the sun. Well, the Earth isn't any different. Okay, the Earth reflects a lot of the light that comes to it, okay, because it's fairly reflective object. Okay, so within the atmosphere, okay, there's different kinds of energy transfers. The main type of energy transfer within the Earth's atmosphere is convection. Okay, so convection involves the movement of particles in a current. Okay, moving air is typically referred to as wind. Okay, so wind is an example of convection happening. Right, so wind occurs for two reasons. It's trying to balance temperature, okay, and energy through the second law of thermodynamics, or it's trying to balance pressure. Okay, usually it's a combination of both. Right, but wind occurs because convection is happening and energy moves from one place to another on Earth through the atmosphere through that process. Okay, convection is the biggest energy transfer mechanism that we use on, or that the Earth uses to transfer energy. Okay. Now, those convection currents can carry sensible heat, that's actual heat, okay, that we could feel, and it can also carry latent heat. Right? Latent heat comes from where again? Right, stuff that's in the water cycle, right? We evaporate water from somewhere and that water vapor moves from one place to another. That's latent heat. Convection also helps to move that, okay? Because convection is, again, the mechanism that gets the air moving. Right, so if we're looking at the three methods of heat transfer, okay, convection would be what you would get around a hot object, like a heater. Okay, so the hot air rises, the cool air descends, and it forms this pattern, this ongoing kind of cyclic current or cyclic pattern. If you have a convection oven, it has a fan inside that causes a current to flow, so there aren't hot and cold spots within the oven. Okay, it transfers the energy to all parts of the oven evenly. Okay, it's why the heating vents in your house on the main floor are on the floor. Okay, that's where the coldest air is. Okay, we want the heating vents to be there because hot air that comes out of them will naturally rise. Okay, now obviously it's blown by your furnace fan as well. Okay, but once it comes through those vents, okay, it's touching the coldest air. It gets a nice convection current happening that helps to transfer the warm air throughout your house. Okay, in your basement, okay, those vents happen to usually be in the ceiling, right? Mostly because you don't want to run vents through the concrete floor, right? If you have underfloor heating or slab heating, like hot water pipes that run under your concrete, then that's more efficient because it's allowing the convection to happen naturally. In the summertime, what do you want to do with those same heating vents on the main floor? Actually, you want to open them all the way up, and you want to close the ones in the basement and just run the fan in your furnace. Because what are you doing? You're cycling the cold air now. Okay. In the wintertime, you want the vents on the main floor. If you have a 2-story house, okay, the main floor vents, okay, or sorry, the top floor vents are not the ones you need open. The heat will go up naturally from the lower floor. Okay, you can have those ones closed and allow convection to do the job for you. In the summertime, you want the opposite. You want the vents on the top floor wide open so that you can blow cold air from below up to the highest point and then have it cycle back down because it's heavier. Okay, so when you're blowing cold air, top vents are open. Blowing hot air, bottom vents open. Okay, that way you can make more efficient use of the energy transfer. Everybody with me on that? Okay, so that's convection. Okay, happens very easily through air because air is the most fluid thing. Okay. Now, in a solid, convection can't happen. For convection to occur, particles have to be able to move past each other, and they can't do that in a solid because in a solid, particles are tightly packed together. So they can vibrate, move back and forth a little bit, but they can't change positions. Okay, they can't flow. That's why you can pour a fluid, but you can't pour a solid. Everybody follow me there? Okay, so in a solid, conduction happens. Okay, and conduction is kind of like a mosh pit. Anyone ever been in a mosh pit? You're missing out if you haven't been. It's fun. But anyway, okay, in a mosh pit, you have people that are tightly packed and they're bouncing around and running into each other, okay, but they're not really switching positions that much. They're just kind of packed in, okay, like sardines, and they're just bumping into one another. Well, that's what it's like if you're a particle or an atom in a solid material. If you get heated up, you move faster, but you're crowded. You can't slide past anything that's near you, so you just run into it more often. Okay? As you run into it, you cause the other thing to gain some of your energy. It's just like, it's just like in the last unit we talked about work. You can transfer energy by movement. Well, you can transfer heat the same way. The particles run into each other. They transfer some of that energy to the next particle and then to the next particle, conducting it along the solid. Now, this isn't very efficient or very fast. Okay? Well, it depends on the material. Some materials will conduct heat very fast, like metals. Okay? That's why you don't want to stir soup with a metal spoon for too long. Okay? You want to use a wooden spoon because if you leave the metal spoon in there, the heat will conduct up the metal and you'll burn your finger. Okay? Wood is a poor conductor, so it doesn't work as well. Okay? So that's conduction, but that only happens in solids. It does not represent a big part of global energy transfers because it doesn't work over long distances and it only works in solids. Okay? Convection, on the other hand, works great. It's through fluids. There's lots of fluids. It can move from one point on Earth to the other through the atmosphere.
How is this?
The thermodynamics part of it. Yeah. We keep talking about energy transfers, right? So not so much the mechanical physics we talked about. This is more the thermal physics stuff. All right, and then the last form of energy transfer is radiation. Okay, radiation is any energy that travels by waves. Right, so it's not just the stuff that turns you into the Hulk. Okay, it's stuff that just travels in waves. Heat is radiation. Visible light is radiation. It travels by waves from one place to another. This is how energy gets to us. Okay, we receive radiant energy from the sun because radiation can travel in a vacuum. It doesn't require a medium to make it go. Okay, on Earth we can use convection because there's matter that can convect. Convection doesn't work in the vacuum of space because there's nothing to move, right? Only radiation can travel through the vacuum of space. So that's what gets it to us here. Now, radiation, okay, that's affected by albedo. It's albedo that determines how much radiant energy is absorbed at any one point. All right, so when we were talking about designing the solar water heater earlier in class, we said we wanted to make it a dark color because dark colors will absorb radiation. once I absorb that energy, I want to get it into the water. Okay, so I need it to move from where it's absorbed and into the water, probably by what process? Probably by conduction. So I'm going to want to make the pipes in the water heater out of materials that conduct heat easily. Okay, things like copper, right? And then I probably want that water to circulate so that it's always bringing water to the area where the sun is striking. That's going to involve using convection, right? So I can harness all three of these heat transfer methods to make something work efficiently. Everyone seeing where we're going with this? Okay, that's an application of the stuff that we've just learned. All right. So, yeah, make sure you know the convection, the conduction, okay, soils and plants through conduction, okay, and radiation stuff. Those are going to be important, okay? So the three things that can happen to light when it strikes the Earth's surface can be absorbed, can be reflected, can be converted by plants, okay? The stuff that's absorbed can be moved around, okay, by convection, conduction, and possibly through radiation, right? That's where all that stuff kind of ties together. All right, hydrologic transfers. So this is energy transfers within the water cycle. We said that was the important part of that was through latent heat, through that evaporated water, okay, and things like that. But there's obviously also ocean currents, which are an example of convection. Okay, so there's convection currents that happen within the ocean. Okay, a thunderstorm is an interaction between, okay, the latent heat of evaporated water, the sensible heat of the area, convection. Okay, all of that kind of stuff is occurring. Right, so the hydrologic transfers occur mostly through latent heat. Okay, so if we're looking at the water cycle in a more simplistic fashion, okay, in order to get ice to turn into liquid, we have to add energy, okay? And then to get liquid water into vapor, we have to add energy, okay? Going back this way, energy is released, okay? So when the water vapor condenses back into liquid water, okay, energy gets released. When the liquid water freezes into ice, energy is released, okay? That's actually why you typically see steam, okay, rising above like a lake in the fall, right? Before it freezes, you'll often see steam rising from, that's evidence that energy is being given off as the water begins to freeze. Okay. All right. Okay, questions on that idea there? Okay. All right, so within the lithosphere, okay, we already said lithosphere transfers, those have to be done through conduction, which only works over small distances. Okay, the lithosphere is mostly responsible for the conversion of energy, okay, from solar energy into chemical energy. Okay, and obviously with the lithosphere, again, that's also where albedo is important. Okay, because it's the Earth's surface that does the vast majority of absorption, reflection, and stuff. Okay, so that's it. We got through it. That's good. All right, so tomorrow, like I said, we're going to be looking at doing this activity to do with climatograms. Okay, so we'll have the Chromebooks. Okay, there'll be some stuff. I'll have the climatograms ready for you for tomorrow. And what you'll have to do is with your group, and you'll be in a group for this. Okay, group those, take those climatograms, and any ones that look similar, put in groups together. Okay, decide whether those groups have similar factors by looking them up on Google Earth to see where they are. Are they all close to the ocean? Are they all close to a mountain range? Similar latitudes, whatever. Okay, put them in groups. Talk about those groups. Talk about the factors that cause the climates to be the way they are. Okay. Then when we come back from Christmas holiday, okay, we're going to hit the ground running and get this unit done. Okay, in probably the next 5 to 6 days after that. So expect that you'll probably have a unit exam middle of the second week back. somewhere around like the 15th or 16th of January. Okay, because we'll get done this unit and then we'll have a couple of days to do final exam review after that. Okay, possibly, not tomorrow. Okay, but you probably will have one that first week back, but then I'll back off because you got to start getting ready for finals. Yeah, it happens fast. Like take your break over Christmas. Yeah, you know, take a break. Okay, but just know that when you come back in January, you got to be able to flip that switch and be on the go because it's gonna come fast. Okay.